Hello and welcome to another video of Grokking the coding interview series, where we are going through the sliding window pattern, and in this video we'll have a look at smallest subarray with a greater sum problem, which is classified as easy. And the problem statement states, given an array of positive integers and a number s, find the length of the smallest contiguous subarray whose sum is greater than or equal to s. Return 0 if no such subarray exists. Okay, and we also have some examples to show how it would work. In this case, in the first example, because of 5 and 2, 5 and 2 are the smallest subarrays which sum to 7 or greater, and in the second case we have a single element 8 which solely sums to greater than 7, and in the third example we have 3 4 1 and 1 1 6 which add to a sum greater than 8. So essentially we just have to find the subarray, the smallest one, which can lead to say a sum which is greater than or equal to s. So how would we approach this problem? So essentially what we want to do is first we want to start say from here, and we want to include elements until our sum is greater than or equal to say s, and once it is greater than or equal to s, we already have the length of this subarray. What we want to do at this point is we want to continue to start shrinking this window until our sum is again say smaller than s, and then we again go ahead and increase the window end to say reach a sum which is greater than s. So essentially how it would work is, and let's do a dry run here. So we start with 2, we add 3, the sum will be 3, we add 5, the sum will be 8. As soon as we are at 8, this sum is greater than say 7. At this point we start moving the start forward, or incrementing the start. So we'll remove this element here. Right now the sum will be 6, so we can which is less than s. So at this point we can start incrementing the window end. So we'll reach a point where it is 1 5 2, which is 8 again, which is greater than 7. We'll start reducing this window. Of course we'll keep a track of the length of this window in the process, but because the sum is greater than 7, we'll start reducing this window, and then we are left with 5 and 2. 5 and 2 is also greater than or equal to 7. We are again keeping track of the length of this subarray, which is 2. So we start reducing this subarray. We remove the 5, we are only left with 2 here, and we see that 2 alone is less than 7, so we again start increasing the window. Here we are again less than 7, which is 5. Now we are equals to 7, and we start reducing the array until we are less than 7. So we'll only have 3 and 2 left, but we do not have any more array to explore or try subarrays there. So our search would end, and we will be left with this solution of 5 and 2, which is the smallest subarray with a sum greater than or equal to 7. I hope the explanation was clear. We also have a visualization below. We'll have a look at it once we are done with our simple implementation. So let's get started and see if we can get a solution. And the idea is in all these problems, we'll try to make sure that our implementation remains as similar as possible. So we can break it into chunks where we know that, okay, here we have all the initializations, here is the condition of expansion or shrinking of the window, and this way we have an intuition around what are the major steps if you're approaching a sliding window problem. So as in the previous example, we initialize the min length. We take the current sum, current length probably, and we also want the window start, and all this will be equals to 0, or actually the min length can be a float of infinity, because here the statement says return 0 if no such subarray exists. So essentially, if in the end we see that our min length is equal to infinity, it would mean that we were not able to find any such array, and we can simply return 0 at this point. So again, the same exercise for window and in range len of array. We want to go ahead. This should actually be sum, and the current sum should be equals to array window end, and here we have something interesting showing up. Like as we spoke, like as soon as our sum goes greater than or equal to 7, we'll shrink the window until our sum is again less than like s. So this is the condition where we'll exercise this. So while current sum is more than s, more than and equal to, because we want to check for both conditions, we'll first see if the min length is actually the minimum, or we have been able to find a new minimum. So min length will be window end minus window start plus 1. In addition, at this point, what we also want to do is we want to, as worked in the previous question, we want to reduce the current sum. We want to reduce the window start from the current sum as we are shrinking the window, and we also want to increment window start by 1. In addition, we also want to check if min length is equals to float of inf. If this is the case, then we want to return 0, else we simply return the min length. And this should give us the answer which we are looking for. Let's do a quick dry run or just a quick walkthrough to sanity check if our implementation is right. So we initialize all the variables, we initialize it to float inf, so we can keep a track if we were able to find any such subarrays. We start iterating through the array. We increase the current sum with the window end element. We check if our current sum is greater than or equals to s. While it is greater than or equal to s, we want to remove all the elements, or we want to keep shrinking the window unless this sum becomes less than s. And the process of removing these elements is simply, we of course want to keep a track if we have encountered a new minimum, and we want to remove the window start element from the current sum, and we want to increase the window start. We want to increment the window start. And as the final check, if the min length is equals to float infinity, then we simply return 0. And this is our solution. Let's try to run it and see if it is in line with what we are expecting. Okay, it seems like it is in line with what we are expecting. Let's quickly speak about the runtime complexity and the space complexity of the implementation. Again, as in the previous example, we are only iterating through this array once, so effectively the time complexity will be O of n, and as we are not saving anything, the space complexity will again be constant space. So let's quickly do this cross check. So this is basically O of n, and the outer loop runs for all the elements, and the inner loop processes each element only once. Therefore, the time complexity of the algorithm will be O of n plus n, which is asymptotically equivalent to O of n, and the space complexity will be O of 1. I really hope you found the explanation clear enough. In case there are any questions, please let me know and I'll make sure to improve it or answer your question. Until the next video, enjoy your day.